Welcome to our first video on section 2.6 in the textbook, where we're going to apply some of the methods that we have learned on systems of linear equations to integration. And in particular, we are going to calculate integrals of rational functions. So we develop a method for calculating integrals of rational functions, that is functions of the form f of x is equal to, so we'll have a polynomial on top and a polynomial on the bottom. Those are what we call rational functions, where m and n are non-negative integers. So the powers here, we are talking of positive powers, and the coefficients are real numbers. So we already know that if we integrate, for example, 1 over x, we get ln the modulus of x plus c, and if we integrate 1 over x plus 1, we get the natural log of the modulus of x plus 1 plus a constant. And if we do the integral of 1 over x plus 1 squared, we do get minus 1 over x plus 1 plus c. And if we integrate x over x squared plus 1, we get half ln x squared plus 1 plus c. And if we integrate 1 over x squared plus 1, we get arctan of x plus c. Right, so what we want is to reduce these functions for some big N to these sort of simpler rational functions that we already know their integrals of. So the strategy is to express a given rational function as a sum of such simpler rational functions, so functions that we already know how to work out. So for instance, we have 2x over x plus 1 times x squared plus 1. So we can decompose it into this. So we have a sum of, we express this as a sum of something over x squared plus 1 and something plus something over x plus 1. X squared plus 1, as you can see, these are the denominators, so that's what we want to be able to do, and then we can then integrate from there. So more generally, a given rational function f such as in 2.11, and 2.11 is the general case that we have there, can always be expressed as polynomials plus terms of the form, and these are the forms that we have. A over ax plus b to the n, and bx plus c over cx squared plus dx plus e to the m, where m and n are positive integers and the quadratic terms cx squared plus dx plus e is irreducible. So in other words, what this means is, so irreducibility means that we can't factor this into, for example, ax plus b and cx plus d, that kind of factorization where the coefficients are real numbers. So we can't do that for this kind, right? Those are the ones that are called irreducible. So the specific form of such a decomposition is determined by the factors of the denominator of f. So the denominator will always determine how we are going to decompose this. So recall that a polynomial function on R is a function p from R to R given by p of x is equal to an x to the n plus an minus 1 x to the n minus 1 up until a1x plus a naught, where n is greater or equal to 0. So we know that this power here is greater or equal to 0, and it's an integer, so it's a non-negative integer, and the coefficients are real numbers, right? So a rational function on R is therefore a function f from R to R given by f of x will be equal to p of x over q of x, where p and q are polynomial functions on R, so what we have just defined, with q not the zero polynomial. So we don't want whatever is below here to be zero, because obviously we can't divide by zero, right? So the degree of a polynomial function p as in 2.12, so the one that we defined here, is the largest integer k such that a to the k is not equal to 0. So here, if we assume that this an is not equal to 0, then that means that um, the degree of this polynomial becomes equal to n, right? And if all the coefficients are 0, so in other words the function is just 0, then the degree of p is undefined in that case, right? So let's look at what equality looks like when we are dealing with polynomial functions. So let n be a non-negative integer, and let p and q be the polynomial functions on R given by p of x is a to the n x to the n plus a n minus 1 x to the n minus 1 plus up until plus a1x plus a naught, and the same for qx but with pn's, right? Then p of x is going to be equal to q of x for every x a real number, if and only if aj is equal to bj for all j. So this is supposed to be a j from 0 up to n. So what it simply means is we are saying the coefficients for p of x to be equal to q of x, it means the coefficients here are equal, right? The corresponding coefficients are equal, right? So let's look at a theorem that tells us how to decompose these polynomials of degree 3. Well, the way the numerator of the polynomial is degree 3, right? So consider the polynomial functions p and q on R given by, so we've got p of x with degree 3, which is so p of x is equal to bx cubed plus dx squared plus ex plus f, where x is a real number, and q of x being equal to x plus a squared plus x squared plus c, where x is a real number, and c, so this c is not equal to 0. In fact, it's greater than 0. You'll see in the proof why we need that condition. So therefore there exist unique real numbers a, b, c, and d such that p of x over q of x is equal to a over x plus a plus b over x plus a squared plus cx plus d over x squared plus c. This is supposed to be small c, right? So, and this happens for every x in for every x a real number, so that x is not equal to minus a. Obviously, if x is equal to minus a, then we have a problem. We are dividing by a 0, so that would be an issue, right? Let's look at the proof. So let a, b, c, and d be real numbers, right? Then what do we have? We have a over x plus a plus b over x plus a squared plus cx plus d over x squared plus c is equal to, so if we do if we take the common denominator, we are going to have x plus a squared, so we are going to have the highest of the x plus a, the highest power, and we multiply by x squared plus c, right? So that will be our denominator, and then So if we say, so if we want to put this one in this form, it means that we are going to say a times x plus a times x squared plus c, right? Because if we divide here, we will be left with a over x plus a. And we do the same for b, and then we get, so the power for b was x plus a squared, so what we get, we are left with this part, so we multiply by that. And then plus cx plus d, its denominator was x squared plus c, so we have to add, sorry, we have to multiply by the whole of that, so that's how we get that. And so if we expand this here, we get that, right? So you can just do that, that little exercise of expanding. So you multiply these two polynomials, you do a product of that, and then you get that. Oh yes, and that is that, and then you do the same for x plus a squared, you get that, right? And then if you rearrange, so you rearrange the coefficients according to the powers of x, so x cubed, so all the x cubed functions, so here we will have a from there, and then we are going to have 1 cx times x squared will be equal to cx cubed, so we have that. So we continue like that up until we have all the coefficients of x cubed, all the coefficients of x squared, all the coefficients of x, and all the constants, right? And where x is a real number such that x is not equal to a, so that is supposed to be not equal to a, right? So therefore p over x, p over px, p over x is equal of, sorry, p of x is p of x divided by q of x is equal to a over x plus a plus b over x plus a squared plus cx plus d over x squared plus c, where x is not equal to a, if and only if. So what we are saying is, because we found this to be, so what we have written here is just what we have there, right? So these two will be equal if and only if the coefficients, the corresponding coefficients are equal, right? So in other words, here we've got bx cubed. So remember what p of x is. It's bx cubed plus dx squared plus ex plus f. So it means for them to be equal, it would mean, so it would mean that p of x would be equal to that expression that we got for every x not equal to minus a. Hence, this is equal to that if and only if the top part, because the bottom part is the same, so we are saying the top part has to be equal. So the polynomial on this side has to be equal to the polynomial on that side, right? And so that's what we have written here. And then what does that mean? That means that if that happens, then it means, so if we take now the coefficients, we can see that the coefficients of x cubed on this, the coefficients of x cubed on this side is b, and then the coefficients of this on the right hand side will be that, and so forth. So d will be equal to that, e will be equal to that, f will be equal to that. So we write that in a system of linear equations, as we all already know. So we've taken the coefficients and we create this system of linear equations, and the variables are a, b, c, and d. And So the coefficient matrix for this system of linear equations will be equal to, so if we take that, the coefficients here, we've got 1 0 because we don't have a b, 1 0, and here we've got a 1 2a 1, and then we've got c 0 a squared 2a, and so forth, right? So we get this is our coefficient matrix, right? So we know that the determinant of a matrix completely determines if the if the if the matrix is invertible, and we can also determine if we are going to get a unique solution, and this is by theorem 5.25. If the determinant is not equal to 0, then we know that we are going to have a unique solution, right? So if we calculate the determinant here, we can use the first row because it has 2 zeros, so that should help, or the second column, it has 2 zeros. You'll find out that the determinant of m is equal to a squared plus c times a squared plus c squared, right? And we know from the hypothesis that c is greater than 0 from the from the from the theorem, from the statement of the theorem. We know that c is greater than 0, and we know that a squared is uh, greater or equal to 0. So therefore it means the determinant is greater than 0, right? So it therefore follows from the theorem 2.5.25, that the system of linear equations in 2.13 has a unique solution. So if it has a unique solution, it means that therefore there exists unique real numbers a, b, c, and d, so that this happens, right? And so therefore that's what we wanted to prove. Thank you. We'll continue with this in the next video.